Deformation of slip. So we have studied about what is defect, that is our point defect, line defect, surface defect, and next is our the deformation of slip. The deformation in our crystal imperfection or the crystal material, the slip is the reason behind it. It is the important reason behind the imperfection of crystal material. So what is slip? Metals deform plastically by slip. Slipping is facilitated in the presence of dislocation. Slip is defined as the process or mechanism by which a large displacement of one part of the crystal relative to another along particular crystallographic planes takes place. There may be one or more slip planes and one or more slip direction in each crystal. Slip begins when the shearing stress acting along the slip planes in the direction of slip exceeds a certain value known as critical slip planes. That critical slip planes are planes of high atomic densities, while the direction of slip along these planes is always the direction of highest atomic density. So, in simple word, cell slip means this is the plastically facilitated in the presence of dislocation in a crystal material. So, see here we are going to see the slip diagram here. So, in material science, the slip planes and associated family of slip direction for which dislocation motion can easily occur and lead to plastic deformation. Here we can clearly say that this is the slip deformation. The both diagram, an external force makes parts of the crystal lattice glide along each other here and changing the material's geometry. Depending upon the type of lattice, material, different slip systems are present in the material. So specifically, slip occurs on close packed planes and in close packed direction also. And the magnitude and the direction of slip are represented by the Burgers vector. We have already discussed what is Burgers vector. This is the magnitude and direction of the slip or the magnitude and direction of the atomic arrangement of a crystal material. The picture on the right shows a schematic view of the slip mechanism, where the slip planes and slip direction in a crystal have specific crystallographic forms. The slip planes are normally the planes with the highest density of atoms that we have read this. Those most closely spaced, and the direction of the slip is in the slip plane that corresponds to one of the shortest lattice translations vector. Often this is the direction in which atoms are more closely spaced. A slip plane and a slip direction constitute a slip system, and a critical shear stress is required to initiate a slip. For the slip, the reason behind this slip system is our shear stress. Slip is an important mode of deformation mechanism in crystal. For metals and technically used in metallic alloys, it by far the most important deformation mechanism and subjected to current research in material system. So, a slip in face-centered cube crystal occurs along the closed pack planes. Specifically, the plane is the type of and the direction is the type of the diagram on the right here. This is our unslipped single crystal fixed at the top end, and this is one crystal after plastic deformation by tensile stress or in the direction of shear stress at the arrow slip occurs on distinct parallel planes. So here is the extension. The rod is like this, from this to this, but after the tensile stress or after a shear stress, this is extended like from this to this. So next is our difference between slip and twinning. So what is slip and what is twinning, and difference between that? The slip occurs discrete multipliers of atomic spacing, where the atom movement are much less than the atomic spacing in twinning. Next is the orientation of the crystal above and below the slip plane is the same after deformation as before. But in twinning, the orientation difference takes place across the twin planes and every atomic plane is involved. In the next point, the slip begins when shearing stress on the slip plane in the slip direction reaches their threshold value called the critical resolved shear stress. But in twinning, there is no critical resolved shear stress and it takes place in a few microseconds. This difference is continuing that the next point is slip lines do not appear during any heat treatment, but in twinning process or in twinning defect, twin lines appear during the annealing operation of a materials. The next point will be the slip lines disappear after grinding or other surface finishing operations. But in twinning dislocations or in twinning defect, the twin lines run through the whole depth of the material and hence do not disappear on grinding or etc. Our last point of the slip will be the slip lines may be present in even or odd numbers, where in twinning defect the twin lines always occur in pairs. So this is all about the difference between slip and twinning. But basically we have differentiated that is what is slip, or that there is definition is there, and what is twinning, their definition is also there. But twinning is the categorization of the surface defect, where the slip is the important reason or important role is fulfilled for the dislocation in crystal imperfection or the defect in crystal imperfection. So next is our effect of imperfection on material properties. So what are the effects when in a crystal material or when in a crystal material have the imperfection or have the defect, like our point defect or the line defect or the surface defect? So what are those effects? It affects the first point, it affects or influence the characteristics like mechanical strength, electrical properties and chemical reactions. The next point of the effect of imperfection, that is the role of imperfection in heat treatment, is very important. Imperfection account for crystal growth or diffusion mechanism, annealing and precipitation. Besides this, other metallurgical phenomena such as oxidation, corrosion, yield strength, creep, fatigue and fractures are governed by the imperfection in crystal material or the material properties. Imperfections are not always harmful to metals. Sometimes they are generated to obtain the desired properties. For our example, carbon is added to steel as interstitial impurity. Here the interstitial impurities means our point defect, that to improve the mechanical properties and these properties are further improved by heat treatment. So it is all about your imperfection of the crystal material and the defects occurred in the crystal material or the dislocation occurred in the crystal material. Thank you.